Hello, good evening, everyone. A very warm welcome to the today's session of Pakistan Catalysis Society. एंड आज के सेमिनार में हम एक न्यू सीरीज स्टार्ट किए जो कि पाकिस्तान कैटालिसिस सोसाइटी एनालिटिक्स ट्रेनिंग के नाम से है, जिसमें पहला हमने थर्मोग्रामेट्रिक एनालिसिस के ऊपर हमने एक जो शॉर्ट वीडियो थी वो हमने अपलोड की थी। और आज के इस सेमिनार के अंदर हम हाई परफॉर्मेंस लिक्विड क्रोमेटोग्राफी के बारे में हम लोग सीखेंगे। और आज के हमारे प्रेजेंटर हैं द प्रेसिडेंट ऑफ पाकिस्तान कैटालिसिस सोसाइटी मिस्टर लुकमान हकीम, who graduated in chemical engineering from Pakistan and bachelor and masters, and now he is doing a PhD from Italy. So after these sessions we will have another session for the question and answers. So I hope you all will enjoy these sessions. So is session now, Mr. Lukman Hakim, please present your lectures today. Thank you so much. And very warm welcome to the Pakistan Catalysis Society online seminar series.
Thank you, Asif, for introducing me. This session is basically regarding some very basics of high pressure liquid chromatography. And we are going to cover some basics of the chromatography, and then we are going to go through some of the equipment components of HPLC. And later on, we can organize some other session regarding the very detailed discussion regarding the HPLC. So let's dive into the HPLC. First of all, going through a bit of the history. So if we look into the history of liquid chromatography, it was basically discovered before the gas chromatography. But the instrumental development of the liquid chromatography was a bit done a bit later than gas chromatography because of the high pressure requirement for the HPLC. And we can utilize this technique for the non-volatile and heat-sensitive substances, and we can quantify the products or the reactants, and based on that, we can get the convergence, reactivity, and these sort of things for our reactive systems, and we can identify the components. So now going through the some of the very basics of the chromatography, how it works, if we have some injector who is going to inject the sample along with the mobile phase into one column, which basically has some stationary phase inside the column. And when the sample basically is injected to the column, it basically interacts with the stationary phase. So based on the interaction, these components, which we can visualize here, are basically separated as we can observe here, like after 5 minutes or seconds, whatever you can say, these are basically separated based on their interaction with the stationary phase. So if we keep on going, we can observe these triangular components are obtained at the exit of the column, while the circular ones are like at the middle, and these are still at the very beginning of the column. So we can say these components are having like most interaction with the stationary phase, while these components are having like least interaction with the stationary phase, while these are having some intermediate interaction. So based on these separations, we can basically identify the components which were like in the form of mixtures. So at the end of the column, we have a detector, and which we can utilize to detect the different components. Like if we want to detect methanol, ethanol, and propanol instead of these like visualized components. So we can use this HPLC, and we can detect those methanol, ethanol, and propanol components using this detector at the end of the column. So now I'm going through the like basic modes of the liquid chromatography. So based on the interaction and based on the columns and based on the different principles, we can mainly divide liquid chromatography into surface adsorption, solvent partitioning, ion exchange, and size exclusion. So we will be going through like each of these type in the coming slides. So let's start with the gas adsorption, like adsorption chromatography. So here we have like stationary phase as a solid adsorbent, and the components are basically interacting with this solid adsorbent, so they can be easily absorbed on the surface of the stationary phase, and some of the components which are like having least affinity, so they will be like passing through the column, and they can be detected at the end of the column. So this basically chromatography is mainly dependent on the adsorption of the components on the surface of the stationary phase. So for this stationary phase, we have different components which we can line inside the column, like silica, alumina. So these components basically have different groups, like silanol groups. So these can very easily interact with the components, and they can retain those. They can slow down those components, and they basically helps us like to separate the components into different components like methanol, ethanol, and propanol, which we discussed as an example in the previous slides. So this basically retains the components and slows down, and basically based on the absorption. So now coming towards the partitioning chromatography. So here we have stationary phase as a liquid that is basically coated on the surface of the solid. So uh, different solute molecules, like they have different solubilities between these mobile phase and the liquid phase that is coated on the surface of the solid. So based on their difference in the solubilities, they can basically be slowed down, and then we can separate them. So basically, there are two modes for this partition chromatography, like normal mode, in which we have polar stationary phase and non-polar mobile phase. So if we are having a polar stationary phase, so based on the principle of like dissolves like, so or like attracts the like, so the polar components will be like attracted towards the solar stationary phase, while the non-polar components will be having like not that much, not any interaction at all. And so we can get those non-polar components at the end of the column, like in the very initial times, and these polar components will be like slowed down, and we can get it separated from the non-polar ones. And there is another mode that is called a reverse phase mode. So in this case, like both of these are like reversed in case of the normal. We have non-polar stationary phase and polar mobile phase. So in this case, like non-polar ones are like retained inside the column, while polar ones are obtained in the very initial times at the end of the column. So now coming towards the ion exchange chromatography. So as it is indicated from its name, so it has basically ionic charge groups at the surface. So it basically attracts and traps the ions, and in this way, it can slow down these ions, and resulting in the separation of these ions. So we call this technique as ion chromatography as well these days. So basically, it works on the interaction of ions inside the mobile phase and ions at the surface of the stationary phase. So based on the interaction, we can separate, and we can obtain the information regarding the ions present inside the sample. So last one is the size exclusion chromatography, and we also call it as GPC, gel permeation chromatography. So how it works basically, we have the stationary phase as a porous media. So based on the pores, the particles present in the mobile phase can either go inside these pores, or if these particles are like big enough, so they can't go inside, and they keep on going, and we can get these bigger particles at the end of the column in the very initial times. While if we talk about like smaller particles, these can easily go inside these pores, and they are like retained. So we obtain these smaller particles by the end of the time. So if we try to obtain the chromatograph, so we can say in this way we can say, so in the very initial times we can get like bigger particles here, and in the intermediate times the intermediate ones, and in the later on times we can get like very small particles by the end of this chromatography. So this is basically also known as gel filtration or GPC, gel permeation chromatography. So we can easily find the retention times of different particle sizes. If we talk about the biomass, we have like oligomers, monomers, and dimers. So we can separate those monomer, oligomers, and dimers based on this technique, and we can get the retention times of those bigger, intermediate, and smaller particles, and we can get the information like how much separation is done inside that chromatography, and we can get the information like how much percentage of the sample is monomers, and how much is dimers, and how much is the oligomers. So now coming towards the polarity, which is very, very important if we are talking about the HPLC. So like I mentioned earlier, like attracts like, and opposites are not attracted towards like polar ones. So based on this principle, we can basically perform the analysis using the HPLC. Like if we are going to use the water, that is very, very polar, and if we are going to use paraffins, those are like non-polar. So based on this polarity and non-polarity, we can analyze our samples in the HPLC. So another concept is like elution process. So what happens in this? Basically, when we inject the our sample using the mobile phase inside the column, so it basically broadens due to different phenomena, which happen basically transversal and longitudinally. So as we observe here, like it is in very narrow time, so as time passes out and it moves down, so it basically gets broadened, so which results in the peak broadening. So we call this as Lewin process, and we are going to discuss different parameters in the coming slides, which can help us to avoid these sort of processes. So now coming towards some fundamental equations, which are like very, very important if we want to discuss about the basics of the chromatography or HPLC. So here we have some sort of like chromatogram. So this is the TM, which is basically the peak for the non-retained solute. And here we have TR, that is retention time for the every solute. Like here we have shown only one solute. So based on these times, we can obtain some important parameters like corrected retention time, which is basically the difference of TR and TM. And using this TM, we can obtain like linear velocity, average linear velocity of the components that are basically flowing down the uh, column. So that is a very important parameter, like average linear velocity. We can decrease this velocity if we want to increase the separation of the components. And there is another factor like retention factor or capacity factor that basically helps us to determine if the separation is poor, slow, or optimum. So based on these times we can, and the velocity, we can obtain this K value, that is retention factor. So we can observe here like if K value is less than 1, so separation is very, very poor. And if K value is greater than 30, so it is very slow separation. And we can adjust different parameters to get our optimum separation that happens in the range of 2 to 10. So there are some other fundamental equations like we discussed already, like average linear velocity. Previously, we can obtain it using the mobile phase flow rate and the cross-section area of the column. And another important intrinsic property of the column is like porosity, which helps us during the analysis, like how much the particle size of the solute we are getting inside. So if porosity is like very very high, so uh, we can break down the mobile phase along with the solute into very small particles, and that can help us like for the better separation purposes. So now, if we consider this column as like distillation column or like adsorption column or absorption column, so we can obtain the efficiency of this column as well. I mentioned earlier, this is Tm for the unretained solutes. This is solute A. So we have retention time for a peak or A solute, and retention time for solute B. So this is the width of the peak at the base for the A component, and similarly goes for the B component. And here you see width at the half height for the A component, and similar goes for the B component. So now we can get the selectivity, column selectivity, based on these retention times of different solutes, which we call as alpha. So if alpha value is higher than one, so which means like separation is good, and we can separate the peaks very easily. And there is another thing, very very important parameter like resolution between the neighboring peaks. So we can obtain it using this correlation. So if this value is higher than one, which means the complete separation of peaks. So if this value is less than zero point 0.8, so separation is not that much complete. We have overlapping peaks, which we can observe here. Like if our S value is less than 0.75, we can easily observe like peaks are not separated here. So if R value is 1, so separation is a bit better than this one, but not that much good separation. So here we can observe like complete separation between the peaks. So if we want to avoid this peak like overlapping or a peak incomplete separation, we can play with these parameters. Like I mentioned earlier, we can slow down the flow rate to change the linear velocity, and we can also increase the length of the column. We can say it as plate height or number of plates as well. If we talk about like separation column, which are basically used in the industries. So they have like different stages. So we can correlate this column in terms of like adsorption column as well absorption column. So we can increase the height to change this separation as well. And we can change the selectivity parameter as well by changing the temperature. So if we basically lower down the damping temperature, we can easily separate these peaks if those components are like having boiling points like very, very near. So we can decrease the damping temperature so that we can avoid this sort of incomplete separation. And we can also play with the like capacity factors, and we can separate these peaks. So how can we obtain like the desired resolution? So we already discussed about the resolution. So we can obtain the column efficiency using the peak width at the base and the retention time using this equation. And we can play with these equations to obtain the R value that basically depends on the retention times and the column efficiency. And we can vice versa obtain it in terms of like selectivity factor and capacity factor. So by playing with these equations, we can obtain the desired resolution. And again, this depends on the number of plates, like selectivity factor and capacity factor, as we discussed in the previous slide. So now coming towards like the actual component of the actual equipment, that is HPLC. We basically initially discussed about the very basics and how we play with different parameters to obtain the better separation and these sort of things. So now we are going to discuss the HPLC equipment. So this is the basic schematic. We have solvent reservoirs, and here we have controller, which basically controls the flow rate and elution. Here we have C, that is basically the pumping component, which basically pumps this mobile phase into this column. And here we have the sample injection. Here we have a pre-column and column. Here we have like a data processing, and at the end of the column we obtain like the solvent, which is a mobile phase solvent along with the sample. So we call it as like a waste solvent. So we have port here to obtain it. So this is the actual picture of the HPLC that is like very, very compact, and we can observe here mobile phase storage that is in terms of some bottles. And here we have different components like HPLC pump, auto sampler. We can put the samples here and it can automatically, we can make a queue and it can automatically analyze these samples, and we have different very very components here like UV lamp and detectors and the processing uh, softwares here as well. So if we talk about the mobile phase, so mobile phase in HPLC is very, very crucial. So a solvent can either be like water, if we are going to use the polar one, or organic one if we are going to use the non-polar ones. So these solvents should be like HPLC grade, which means like purity should be very, very high, and these should be like pre-filtered to avoid any sort of damage to the pumps and the columns. So that is very, very important step, like pre-filtration column and prior filtration. This is very, very important step inside this HPLC. So now we can discuss about the different components a bit. We have like a pump that basically takes this solvent and injects it inside the column. So it is basically reciprocating pump. So for those who don't know about the principle of these reciprocating piston pumps, it basically creates a suction when it moves in this direction. So here vacuum is created, so it gets the sample inside from this port, and when it reaches here, it basically, this is motor, so it pumps it back in this direction. So pressure is basically increased, so this basically port opens and we inject the sample to the anywhere in the HPLC. So here we have injection system in the inside the HPLC. So it basically depends on the type of HPLC. So we can have like 6-port valve, which is utilized for the injection purposes. So it basically takes the mobile phase, and it also takes like the sample, and it basically injects both of these like mobile phase and the sample to the HPLC column. So here we have HPLC column that we can observe here inside this picture, and we have end fittings to fit it inside the equipment. So this is very, very tiny column actually. So we have stationary phase inside it. So this is also very, very delicate. So we basically use different sort of packings inside, as we discussed previously, to get the better separations. And uh, over the decades, like with the improved packing techniques, we have obtained like the efficiency has been improved with these columns. So last part is the like detectors inside the HPLC. So we can utilize different sort of detectors like general or bulk property detectors, which basically works on the physical properties of the components, and we can have some solute property detectors as well, like spectrophotometric detectors, which are basically specific to the solute, and we can couple this HPLC with the mass spectroscopy as well, and the infrared spectroscopy as well, for based on our solute components and based on our the uh, understanding of the equipment, we can couple it with the couple of detectors for the better understanding of the system and these sort of things. All right, thank you. That's all from my side. If you guys have some questions, so we can either go to the other session or we can continue here.
Thank you so much, Mr. Lukman Hakim, for a nice presentations, and it was a enjoyable and very nice talk. So maybe we have a less time here, so we can join another sessions where we can have a discussion about this presentation, and we have another presenter on the same topic. So let's move all participants to the next sessions, and let's have a fruitful discussions and another presentation from Mr. Abdul Jabbar. Thank you so much for all.